Welcome back to linear algebra. In this video, I want to talk a little bit about the idea of orthogonality. And more generally than orthogonality, we're going to be talking about the angle between two vectors in an abstract vector space. In the 2- and 3-dimensional Euclidean vector spaces, the angle between two vectors is a very reasonable thing to talk about. We can picture very clearly that if I have two vectors in the plane or vectors in space, I can figure out an angle between them. It turns out that we can do that in general, and we can define an angle between vectors in abstract vector spaces as long as there is an inner product defined. And once we have an angle defined, we can start looking at the special case of a right angle. Two vectors are orthogonal if they have a right angle between them. So let me get my head out of the way and let me remind you that the definition in the Euclidean vectors of the angle between two vectors is that the cosine of the angle is equal to the dot product of those vectors divided by the product of the magnitude of those vectors. All right, that's true in any Euclidean n space. In general, in any inner product space, the Cauchy-Schwarz inequality gave us that the magnitude of the inner product of u and v is less than or equal to the norm of u times the norm of v. And so if I divide both sides of this equation, or inequality, I get that the absolute value of the inner product of u and v divided by the norm of u times the norm of v is less than or equal to 1. And having that less than or equal to 1 is important because cosine is defined to give angles, for any angle, cosine of theta is defined to be between -1 and +1, excuse me. And so we can define for any inner product space, the generalization of the dot product is the inner product. The generalization of the magnitude is the norm. So define the angle between vectors in any vector space as the inverse cosine of their inner product divided by their magnitude. And we say that two vectors are orthogonal if this angle comes out at pi/2 or 90 degrees, a right angle. Knowing what we know about the inverse cosine gives a result of pi/2 if and only if the argument is equal to 0. And so, if norm of u and norm of v are not 0, which remember is equivalent to saying that u is not the 0 vector and v is not the 0 vector, we can simplify this further and get that two vectors are orthogonal if and only if the inner product of those vectors happens to be equal to the 0 vector. I'm sorry, 0 as a scalar, I'm getting ahead of myself. The inner product of u and v is the real number 0. For the cases where u itself or v itself is the 0 vector, there are two schools of thought. Some people, some applications find that it is incredibly useful to have the 0 vector orthogonal to everything. Some cases, some applications say that it is convenient to have the 0 vector orthogonal to nothing. For our purposes, it's not really going to make that much of a difference. But because sometimes it's useful to just decide that the 0 vector is orthogonal to everything, we want to not worry about the special case. We can separately define that the 0 vector is orthogonal to everything. And in that case, we don't need to distinguish u non-zero, v non-zero. We can just have when the inner products of the two vectors is 0, the vectors are called orthogonal. So the inner product defines the geometry of the vector space. It defines what it means to be a right angle and what it means to not be a right angle. The Cartesian coordinate plane that you're accustomed to has a right angle because we define the Euclidean inner dot product as the inner product to have that angle. There are other coordinate planes where we define the dot product to end up with a slight shear to it, and that's perfectly fine. I want to take a look at orthogonality of polynomials. So we saw in the previous video that the integral from -1 to 1 f of x g of x dx forms an inner product space. And because this is an inner product space, let's consider a couple of vectors here. How about x and x squared? Well, we can take a look at the norm of f, that's the integral from -1 to 1 of x times x dx, using the power rule. We're integrating x squared, which gives me 1/3 x cubed. 1/3 times 1 cubed is 1/3 minus -1 cubed is -1. So 1/3 times -1 is -1/3. The norm of f in this inner product space, the norm of x, is 2/3. I'm sorry, I forgot to write something down. I jumped ahead of myself and made a mistake. The norm of f is the square root of the inner product of f with itself. So we need the square root every step along the way. Sorry about that. Square root of 2/3 is the norm of the vector x. But orthogonality, different question. I encourage you to take a look at the norm of g. Go through, perform the integration. It's a fairly straightforward one. But I wanted to go through and point out that neither of these vectors has a norm of 0. So it might be interesting to talk about. But what happens if I want to take the inner product of these two vectors? Well, that's the integral from -1 to 1 of x times x squared. All right, x times x squared is x cubed. Using the power rule for integration, this is going to be 1/4 x to the 4th, evaluated at -1 and at 1. So that's 1/4 times 1, which is 1/4, minus -1 to the 4th is 1. 1/4 times 1 is 1/4. So in this particular inner product space on polynomials, the function x, the vector x, and the function or the vector x squared are orthogonal. In Calculus 2, you learn about Taylor and Maclaurin polynomials. And it turns out that the reason that Taylor and Maclaurin polynomials work and are useful is because this is the norm of functions that we care about, or something very similar to this is the norm of functions that we care about when we're talking about Taylor and Maclaurin polynomials. And each of the pieces, each of the terms is orthogonal to the others. So there's a lot of application just right in that. Now let's get to some interesting Let's let V be any inner product space, and let's take W a subspace of V. And then we're going to create a new set, which is called the orthogonal complement. We're going to denote it as W with the perpendicular symbol, kind of looks like an upside down T. And this is the set of all vectors in V such that the inner product of V with W is equal to 0 for all W in the vector space W. Putting that in words, we are looking at the set of vectors which are orthogonal to every vector and I claim that the orthogonal complement is also going to be a subspace. Right? To show that something is a subspace, we have a couple of properties we have to keep in mind. It has to be a subset of V, and from our definition, right, the orthogonal complement is a set of vectors in V. So by definition, this is a subset of V. It has to be non-empty. And as is often the case, to show that a set is non-empty, you don't have to specifically show that it's the zero vector in there, but the zero vector is in every vector space, and it's very often the easiest one to show. Here, we know that the zero vector, inner product of zero vector with W is equal to 0 for any vector W. And so because of that, 0 is always in the orthogonal complement. The orthogonal complement is not empty. And then the last thing we have to show is that the orthogonal complement is closed under addition and scalar multiplication. And here we start to run out of variables to look at, but let's let U and V be in the orthogonal complement, and let's let W be in the set we are basing off of. And we're going to need a scalar K as well. Well, the addition U plus V, we can split up, right, using the additivity of the inner product. This is U with W plus v with w. And since u and v are both in the orthogonal complement, the inner product of u with w is 0, and the inner product of v with w is 0. So u plus v is in the orthogonal complement. Similarly, if I take ku with w, using the homogeneity, this is k times the inner product of u with w, and the inner product of u with w is 0 because u is in the orthogonal complement, and a scalar times 0 is equal to 0. So orthogonal complement is also closed under scalar multiplication. And those are the things we need to show in order to claim that what we have is a subspace. And so we have it. If we have a subspace, we can take its orthogonal complement, and that will also get us a subspace. Taking a slightly different approach, the orthogonal complement of a set forms a set, and that's one way to talk about a set being orthogonal. And it is an interesting way, but it's not the only thing you might mean. Let's let V be any inner product space, and let's take a subset, right? I am not this time claiming that this is a subspace. It's just a set of vectors. We say that S is an orthogonal set if for any pair of vectors in the set, the inner product of those vectors is 0. That is to say, any pair of vectors in the set is orthogonal to each other. To throw an extra condition on, if we have an orthogonal set, and it is further true that the norm of every vector in the set is 1, we have what's called an orthonormal set. It's an orthogonal set that has been normalized. putting that into terminology, if we take any vector v and we define a new vector by dividing v by its own norm, then the norm of that new vector is going to be 1. And this process of creating a vector we call normalizing a vector. So if we have any orthogonal set, it is incredibly straightforward to turn that into an orthonormal set. And while having orthogonal is nice, having orthonormal is even nicer. Once again, I want you to think back to the Euclidean vectors. And the standard basis in Euclidean n-space forms an orthonormal set. So the idea here of an orthonormal set, we will see next time, is going to allow us to extend some more nice properties of the unit vectors in Euclidean n-space into other vector spaces. For now, I know it was a pile of definitions to throw at you, but just knowing that this is a thing and knowing that we can do it is good enough. So take a look at some of the practice problems involving orthogonality and identifying orthogonal vectors, and I'll see you in the next video.